So, quick summary, we had our process planned, we had our zero order hold block in order to discretize the system, and we started here with a proportional controller. So the transfer function we achieved here was Ts squared, where Ts is the sample time times z plus 1 over 2 times z minus 1 squared. We defined the sample time to be the square root of 2. This simplified our expression a little bit more, so that we finally had z plus 1 over z minus 1 squared. So this is 1, 0, and 2 poles. The 0 is located at minus 1 on the real axis, and the 2 poles are at plus 1 also on the real axis for, let's say, the open loop transfer function. The controller is a simple proportional controller for the transfer function k. So what did we do? We wrote down the characteristic equation, 1 plus kg equal to 0, which is used to determine the poles of the closed loop system. And we put in the transfer function g of z, so that we had a second order polynomial in z, and with a related formula we could calculate the location of the closed loop poles as a function of our controller parameter k, which is part of the formula. So that means using our controller parameter k allows us to push the poles along some branches in the complex domain, and to place them where we would like to have them in order to define the dynamic system behavior as we intend to do so. So we calculated the root locus curve, and we learned how to draw the root locus curve manually. The root locus curve contains some breakaway points and re-entry points. So as soon as the branches of the root locus curve leave the real axis, this is a breakaway point. And then when the branches come back together at the real axis, these are the re-entry points. So for this specific example, we were able to draw a root locus curve that looked like this. So here we have the unit circle, and this is the location of the 2 poles of the open loop transfer function. So every root locus curve starts at the poles of the open loop transfer function, and the branches end at the zeros, or if there are not enough zeros in relation to the poles, then the branch will end at infinity. So here we have just 1 0, so one branch ends at the 0 of the open loop transfer function, the other one will go to infinity. The closed loop system poles move along these branches when we change the k, our controller parameter. So here the poles start for k equal to 0 at plus 1 on the real axis, and then if I increase the k, they move along this circle, then they come back here on the real axis, and one is going to the 0 and the other one is going to infinity. We're changing the parameter k. So for this specific system, we saw that it is actually impossible to have a stable system behavior with just a proportional controller, because the branches are completely outside the unit circle. With a proportional controller, it was not possible to have a stable system behavior. It will be unstable for any k. So that means we have to change something in the controller structure in order to push the branches into the unit circle. Because we know from the mapping that the left half domain the Laplace domain will be mapped into the unit circle. So all of the poles of the closed loop system have to be inside the unit circle to have a stable behavior. And knowing the rules for the construction of the root locus curve enables us actually to have some design idea how to get there. So we know when we construct the root locus curve that the real axis left of an odd number of poles and zeros is actually root locus. So that's one rule. The next rule is that the root locus curve is symmetric to the real axis. And then we learned about the calculation of the breakaway and the re-entry point, but just this one rule about the real axis allows us already to have some thoughts about how to get the branches into the unit circle. So we can change and modify the controller with some poles and zeros actually. Then these new poles and zeros belong to the open loop transfer function. And if we do so, for example, we can put 1 0 here on top of the poles. Then we have, instead of 2, we have 3. And that means left of this bunch of 3 poles and zeros, the real axis will become root locus. And if we add another pole a little bit left on the real axis, then we have a predefined part of the real axis to be root locus, and that automatically pushes the breakaway point here to the left. And then the branches are completely, well, not completely, but they go through the unit circle, and we have a nice area where we can place the poles in order to have a reasonable, stable system behavior. So this understanding how to generate, how to design the root locus curve allows us to design the controller in the end. And then the final values can be found using the control system designer in MATLAB. So this is then the new controller structure that we used, C of z, z minus a over z minus b, so 1, 0, and 1 pole. Okay, and then, for example, we put the 0 on top of the 2 poles from the process plant, and the new pole a little bit left on the real axis, and then we have a nice closed loop system behavior. So let's show that again in MATLAB, and then we can have a look at some additional aspects. So Zizo. Okay, so Ts is equal to square root of 2, so 1.41, and then our transfer function G is equal to Tf, and here we had z plus 1 over z minus 1 squared. So the numerator z plus 1, we have the coefficients 1 and 1. And z minus 1 squared means we have 1 times z squared minus 2 times z plus 1. And the sample time is ts. Okay, so this is our process plant. And then we go to edit architecture. And here for our G, we choose G from the workspace, click import OK. And then we have the root locus curve, similar to the one that we've drawn manually. The 2 purple dots are the closed loop system poles. We will not be able to get them into the unit circle with a proportional controller, so we make a double click to the controller itself and then add 1 0, a real 0, and put it to the location +1. And then we add an additional pole, real pole, and push the pole to 0.2, for example. Then we have to adapt the scaling in order to see something. And here we go. The breakaway point moved into the unit circle, and this way we have the possibility to get the closed loop poles into the unit circle and get a stable system behavior. In order to do that, I decrease the value for C. So when we see the poles already, now I grab one and push the conjugated complex pole pair into the unit circle, and then we see the step response to the reference step, and it's a damped oscillation with the sample time, 1.4 seconds. Now we can remember that we had a look at the requirements, so there is the possibility to set the requirements in terms of overshoot and damping and so on. If we display a grid, and this is maybe an additional interesting aspect, we see something like this. So the lines that are displayed here in the root locus curve in the complex domain are actually lines of constant damping and lines of constant natural frequency, omega 0. And it's also possible to calculate those lines in the following way. So if we remember the situation that we have for continuous systems, then for example a BT2 system has this transfer function here, k over second order polynomial in the denominator. So we have 1 over the natural frequency squared times p squared plus 2d over natural frequency times p plus 1. So k is the amplification factor, omega 0 the natural frequency, and the damping factor capital P. So if we have a look at the conjugated complex pole pair in the complex domain, here we see one example. Then sigma is the real part, and j omega the imaginary part. So sigma is actually the inverse of the time constant of the exponential function, which connect, let's say, the amplitude, the maxima of the amplitude of this sinusoidal output signal, which oscillates with an angular frequency according to the imaginary part. And omega 0 is the length of the phasor, that's the natural frequency. This is actually the frequency the system would oscillate with if there would be no damping at all. So the length of the phasor, and the damping itself is the cosinus of this angle C. So that means that lines of constant damping were in the continuous case just straight lines going into the origin, because then the angle on a straight line going through the origin would remain constant, so the damping would remain constant, and the lines of constant natural frequency would be circles around the origin. Yeah, so this is actually the situation here. Down below we have the poles written with d and omega 0, and the length is omega 0, and d is the cosinus of this angle c from the real axis to the pole phasor. Okay. And now if we do the conformal mapping into the z domain, we end up having something like this, because the ratio or the relation between z and p is this one here. Z is equal to e to the power of p times capital T, where t is the sample time. So we can rewrite it as a phasor with the length e to the power of sigma t, real part, times e to the power of j omega t, where omega t is the angle. And if we put in for sigma and omega the related expressions from the slide before, we get e to the power of minus d omega t times e to the power of j omega 0 times the square root of 1 minus d squared t times t. And if we vary omega 0 t, then we have actually the lines of constant damping in the z domain, which are these ones here, the colored lines. So you see the legend showing d equal to 0, the undamped system, up to d equal to 1, where we have an aperiodic behavior. The system is not oscillating at all anymore. That's the border. Yeah, so these are actually the lines of constant damping, and if we go back to MATLAB, then this is what you see here inside the unit circle. Yeah, the other ones are the lines of constant natural frequency. Okay. Good. Any questions about that? Yeah, I mean, the way to define certain requirements is the same. You can make a right click here, and then you get into the local context menu, and here is design requirements. New will open up a little window, and there you can pick again settling time, percent overshoot, damping ratio, network frequency. So all the requirements that you like, and then you can separate the whole complex domain into a yellow forbidden area and a white area where you have to place all the folds in order to fulfill the defined requirements. Any questions about that? Not the case. Let's come actually to the last chapter of these lectures, and I hope we still have some time to have a look at an example exam, so that you see the structure and how it looks like, especially concerning the digital control part. So the last chapter is actually about quasi-continuous design of digital controllers, and the way to calculate the formulas in the Z domain for the controller. So there are quite a lot of different procedures to get from the continuous case to the digital case, if the condition is fulfilled that the sample time is small enough compared to the smallest time constant in your system. So an order of magnitude better, let's say. And here is the list. You have Euler, backwards and forwards. Then you have a so-called bilinear transformation, and some more. Today we will concentrate only on Euler and the bilinear transformation, and see how it works. In the end, all the methods are similar to each other, and if you decrease the sample time more and more down to 0, then actually they will merge to one common behavior, which you can see here in the Bode diagram for the controller. So especially at high frequencies, you have the differences in the magnitude and in the phase, and also the step response will merge down to the continuous step response if you lower the sample time more and more. Okay, so let's start with Euler. So how does it work? I open my Adobe annotator. New. Okay. We talk about quasi-continuous design of digital controllers. That means TS is much smaller than, let's say, T, where T is the smallest time constant in the system. And we start with Euler. And here we have backwards and forwards. So let's start A with Euler backwards. How does it work? So if we have a look at the derivative, dx over dt over the signal, then Euler says that the limes of delta t going to 0 of x of t minus x of t minus delta t over delta t is actually approximately x of k times capital T, Ts, let's say, the sample time, minus x of k minus 1 times Ts over Ts, sample time. And now in the Laplace domain, the derivative is a multiplication with the Laplace operator p. So x of p times p will be, according to this Euler backwards formula, will be 1 minus z to the power of minus 1 over Ts times x of z. So let's mark it with a color. So here we have x of kTs. This is what we have 1 times. And then the right shift here in green, x of k minus 1 times Ts. In the z domain, this is a multiplication with z to the power of minus 1. If I multiply the value with z to the power of minus 1, then I shift it actually to the past by 1 times that. And the Ts is in the denominator. So we can also write it as if we multiply in the numerator and in the denominator with z, let's say this way, v over z, and we didn't change anything, but we have z minus 1 over Ts times z. And this is actually the substitute that we can choose for our P. So let's assume that we have a PI controller. And the PI controller has the continuous transfer function Gc of P is equal to Kp times 1 plus Tn P over Tnp. So that would be a PI controller. They have a proportional and an integral part. Then this Euler backwards definition would allow us to get to a d of z, which is equal to Kp times 1 plus Tn. And now we substitute the P with this expression here. So T times Z minus 1 over Ts Z And then we have TNP, so Tn times z minus 1 over TSZ. So that's the substitution here. And then finally we can eliminate the double fraction. If we do that, we get Kp times 1 plus Tn times z minus 1. And the TSZ, oh sorry, if I extract the TSZ, then it stands here, TSZ, where the 1 was. And then I can put it down to the denominator where it is cancelled out, so I have here Tn times z minus 1. Okay, so let's assume some values. So for example, Kp equal to 3, that's what I have here. Tn is equal to 2 seconds. And then Ts is equal to 1 second. Then we have d of z is equal to 3 times, and here in the numerator we have Ts, Tsz plus Tnz. So Ts plus Tn is 3. Let me quickly check, is that correct? I took out this. It's there. Yeah. 2 plus 1 is 3. And then we have Tn times minus 1. Tn was 2. So minus 2. Here we have T and Z is 2Z minus 2. Okay. Now the question is, if we have such a system with the transfer function b of z, we have to implement it into our software. Then the input is actually the error e, and the output is our actuating signal y. So the d is actually output over input, so y over. And then we can finally get the equation that we need to put into our software. So we have y times 2z minus 2 is equal to, 3 times 3 is 9. Z minus 6 times e. And if we multiply with z to the power of minus 1, then we get finally y times 2 minus 2z to the power of minus 1 times y is equal to 9e minus 6e to the power of minus 1 times e. And this means finally that let's divide it by 2 again, then we have y minus e to the power of minus 1 times y is equal to 4.5 e minus 3 z to the power of minus 1 e. And that means the new value of y at the time k times sample time ts is equal to the new error 4.5 times the new error in k minus the old error 3 times e k minus 1 plus the old output which you have to store in the memory, so that's plus y of k minus 1. Because here on the left side it's with a minus, so it goes to the right with a plus. So this is the final equation that you have to program in your software. Question?
Yes, how do we come from these c to the power of minus 1 to e of k minus 1?
Okay, so remember, the multiplication with z to the power of minus 1 means actually, so y is the value, and this exponent here tells you the point of time when this value is applied. That's what we learned several lessons ago. So yeah, so minus 1 means one step into the past. The same here. So y of k minus 1 means that k minus 1 times the sample time ts. K is the newest value that you calculate, in this case yk. In order to calculate the new value for y at the output of the controller, you need the actual value of the error multiplied with 4.5. You need the old value of the error from your memory, and you need the old value of y that you store. Yeah.
There was a variable called TNP. What was that?
Tn, p is the Laplace operator.
Ah, okay. Oh, I thought it was in the index. But okay.
No. No, that's yeah, multiplication. Okay. So that was Euler backwards, but Euler backwards defines only the substitution that you use for p. So when you get from the p domain to the z domain. So if we go to b, Euler forwards, then the definition is slightly different. because then the derivative, dx over dt, is defined as x of t plus delta t minus x of t over delta t. And this is approximately x of k plus 1 minus xk over ts. And that means that now the new substitution of p is going to be so xk plus 1, so that's a shift into the future, so a multiplication with z to the power of 1, so I get z minus 1 over ts. And this is your new substitution. You can do the same calculation as above with the Euler forwards, and then you have a slightly different result for the transfer behavior and also for your code that you have to program. I don't want to repeat that again. Maybe as the last example, we can have a look at the bilinear transformation. From Tuscan. This can be also put here in MATLAB if you're if we have a look at the command C2D. C2D continues to discrete for the transformation of the system. And click help. Then we have the possibility to, so we can provide in the round brackets the system and the sample time, but also the method. And here you see the different methods that are possible. Zero order hold as a standard default method, but also Tuscan, for example, can be chosen. And Tuscan is actually the bilinear transformation, which is quite often used because it delivers good results. And maybe a few words about the background here. So actually it's all about the definition of z, which is e to the power of p times capital T, the sample time, or ts. So we can solve this equation for p, and p is then 1 over t times the natural logarithm of z. So this is the result that we get when we solve for p. And the development of the natural logarithm into a power series looks like this. Into a power series. Looks like this. P is equal to 2 over t times, and then curly bracket, and we have z minus 1 over z plus 1 plus 1/3 times z minus 1 over z plus 1 to the power of 3 plus 1/5 times z minus 1 over z plus 1 to the power of 5 plus and so on. It's an infinite power series, and if you break up after the first term, then this is the substitute for the bilinear transformation according to Tustin. So what you use now here is so the substitution for p is 2 over t times z minus 1 over z plus 1. This is quite often used in the literature, and you also can pick it here in the method for the transformation. And then for the PI controller, calculation would be quite similar. You just take the different substitution, put it into your controller equation, and then you get your d of z, and finally you can write down the software equation that you need to implement. And there are many more. If you reduce the sample time more and more, then in the end they will all lead to the same result. But if you design the controller in a discrete way, then can sometimes be helpful to play with the different approaches to get the best result that you would like to achieve. Okay. Any questions about that? Then this is actually it concerning the content of the lectures. So let's have a look at the exam. There is one sample exam. So in general, we have 10 questions for advanced control theories. It's going to be 6 questions related to the state space control from Professor Kerber, and 4 questions concerning the digital control part. And here I would like to show you the structure of the digital control part. So all the individual chapters are covered. Maybe if we start with what you're allowed to use. So the only thing that you will get is this appendix here with the conversion table. There you have the 3 columns with the time domain, the Laplace domain, and the Z domain. Here you have the different rows with some examples so that you can use the table for translation between the domains. Other than that, okay, here are the rules related to Z domain and time domain. These are also part of this appendix here. This is what you will get, and furthermore, you're allowed to use a non-programmable calculator. So that means that you need to know some of the definitions by heart. Here are some examples. So for question 1, you will always see how many marks you can get in total, and also the individual marks per question. So one question is here, for example, what is the definition of the Z-transform? Give the equation. Give the relation between Laplace operator P and Z. So Z is equal to e to the power of pt. Which is this transfer function of the zero order whole block in the P domain? So everything we discussed on the slides, basically. Then what else do we have? Here we have the zero order hold method to get the staircase function with a continuous process planned. Here the transfer function Gp of P. Gp is given 1 over P squared. Sample time is given, and then the task is to calculate the Z transform G of Z for the dynamic system according to figure 1. So how does that work? What would you have to do here? Just you don't need to do everything again, but just to name the process steps. What is necessary here? So G of Z is the product of the two transfer functions, so K times GO times GP. So it means you need to know GO for the zero order whole block. And then it is 1 minus Z to the power of minus 1 over P. Then you can put the P to the process plant. Use the method of the partial fractions in order to have the terms that you need with this translation table in the appendix. And then you can do the direct translation of the individual terms. And finally, you have, with the help of the appendix of the translation table, you have the Z transform G of Z of the total transfer function. What else do we have? Calculate the first 3 values of the output Y of KT for an input X of Z equal to 1. Okay, so we have the system here with the transfer function G of Z. We know the input, so we know the output is input times transfer function. And if we need the first 3 values of the output, we have the Z transform. What do we have to do? The transfer function is a numerator over denominator. Polynomial division. Yeah. So here you would have to do a polynomial division, calculate the first 3 values of Y. Okay. Then question 2, 8 marks. The closed loop transfer function of a digital control system is T of Z is G over 1 plus G, with G equal to, and then we have here numerator over denominator. Sample time 1 second. So this closed loop transfer function can be calculated by putting in the G into this expression. And then the question is the closed loop stable for K equal to 1? So K is here, this parameter, and G is the closed loop stable. So what would you have to do now?
Plug in K and then determine the system poles and look whether they are like in the left half plane of the
No, now
or
we're
in the unit circle.
In the unit circle?
Case, yeah.
Exactly. Correct. So for the continuous case, we would have to have a look at the poles are all in the left half domain, but here the new thing related or compared to the fundamentals of automatic control is to have a look if they are within the unit circle. And that means, what is the condition for the poles to be within the unit circle? Means that the phasor length of each pole has to be less than 1. This is the case. So you calculate the absolute value of the phasor length here, and if it is less than 1, you know, or for all of the poles, then you know closed loop is stable. Okay, equal to 1. And then the following question, for which k does the system become unstable? Become unstable means we're looking for the stability border. So what is the approach, what is the condition that we have to write down in order to find the related k for the stability border?
Yeah, phasor length equal to 1.
Phasor length equal to 1, correct. And then solve for k. 4 marks. So what else have we here? Question 3, 10 marks. The transfer function of an analog PI controller is given by. So that's actually what we just calculated. So we have the PI controller. Here's the transfer function. Some values are given. K is equal to 40, n is equal to 2 seconds. Sample time 1 second. Then calculate the Z transform. Word is missing, I don't know why. But calculate the Z transform D of Z according to the procedure called bilinear transformation testing. And here is a hint, as a reminder to this infinite power series that we just discussed. And Tustin says that the first term for k equal to 0 is enough for the substitution. So you pick 2 over t times x minus 1 over x plus 1. Substitute the p in the controller function and solve it, and then you have d of z. Eliminate the double fraction, and then you have the d of z. Then you get another controller, d of z. So if you were not successful at this point, you will still be able to jump in to the question with an intermediate result here, which is the equation that has to be used in order to implement the controller algorithm according to d of z on a microcontroller. Okay, so if this is the controller function, how does the equation look like that you have to put into your code?
We can use a TF, then enter to the numerators 3 to negative 2.5 plus. Sorry, 3 negative 2.5, yeah, 0.5, close parenthesis to the other 1 negative 3, and 2.
Yeah, so correct. So actually, this d of z is equal to y over e. Y is the output of the controller, e, the error is the input of the controller. So y will come together with the denominator, and the e will go over to the other side with the numerator. And then actually we can multiply the whole equation with z to the power of minus 2. And then we have the placeholder. We have then y over e, so we need 3 times the actual error, minus 2.5 times the old error, plus 0.5 times the error before the old error, and then plus The minus will go with plus to the other side. 3 times the old actuating signal, and then the second old times minus 2. That's the equation. And then the last one, what happens during operation of the sampling period if the sampling period is significantly different from the one used to calculate d of z due to missing real-time conditions, smaller or bigger? So if I have defined here 1 second, and then I implement the controller on my microcontroller, but due to the fact that I don't have a real-time operating system, the 1 second is not guaranteed. So, for example, if I put the equation into the ordinary while zero loop, and it's going to be calculated much more often, much faster than the 1 second. So it would be the case it's smaller, and if for whatever reason computational power is not sufficient and I need more time to calculate the equation, and it's maybe higher than the 1 second. So what are the consequences here? If I'm running the equation too fast or too slow, what are the consequences? Correct.
Because if the t is not stable, it acts like a moving k, and for moving k we can get unstable.
Mm-hmm. Yeah, it's like having wrong controller parameters actually, because the controller parameters we've seen that they're mixed up with the sample time to one number in your expression. So it doesn't matter if you have a wrong controller parameter or wrong sample time. In the end, it's the same effect, and it's the same effect even if you are faster. So people sometimes tend to think, oh, if I calculate the equation much faster than the 1 second, and everything is even better. That's completely wrong. If you define the sample time to be 1 second, and if you calculate your equation faster, maybe in 100 milliseconds, then you have to wait another 900 milliseconds until you're allowed to calculate it the next time. That's very important, not to think, oh, I'm even faster, so it's better. It's not the case. So if you define sample time to be 1 second, then you have to stick to it, and you have to wait if your computer is calculating faster. Yeah, so otherwise you have the same effect as if you have wrong controller parameters. So in both cases, smaller and bigger. Okay, and then the fourth questions for digital control, we only have 4 questions. Here we have a closed loop control system with a reference input R, error E, actuating signal Y, and the output here that we would like to influence X. The process plant is given here, G of Z, actually similar to the example in our slides in this case. And the controller transfer function is given, sample period, sample time is given, and the tasks are calculation of the closed loop transfer function T of Z. Okay, so how does that work? What's the closed loop transfer function here? So let's just name t of z as a function of d and g. Yeah.
Was it 1 plus t divided by t or something like that?
No. So it's always the transfer function in the forward path over 1 plus the transfer function in the forward path times the transfer function in the backward path. So we have dg over 1 plus dg. And then we can put in the individual expressions here to calculate t of z as a function of z. So dg over 1 plus dg. Okay, then where do the branches of the root locus curve start and where do they end in general? So here everything is related to the rules to draw a root locus curve. So branches, they start at the poles of the open loop transfer function and they end at the zeros or infinity. There are less zeros than poles. Which parts of the real axis are root loci? So if you're left of an odd number of poles and zeros, then the real axis is root locus. Calculate breakaway and re-entry points on the root locus curve. How are they calculated?
And we represent the poles as a function of k, then we take the square root of part, which is the square root part, which is the only part that can be possibly complex, and equate that to 0.
Correct. And then in the end, the root locus curve has to be drawn in the z domain as a function of k. Yeah. So this is how the structure looks like and how the questions could look like. Do you have any questions about that?
Are there any more past papers to revise from, or is it just those ones?
They are all pretty similar
Yeah.
from the structure point of view. I think with the 4 questions and the sub-questions, we cover actually everything that we've discussed here in the lectures. So.
Is there much variation in the questions?
What's the variation?
Yeah, is there much variation?
There is some variation.
Some variation.
But that's all I can tell.
Okay.
Any other questions?
Are you going to do like a revision class before the exam or
A revision class?
Yeah.
Oh, that's not planned. So if you have any questions, just send me an email. Okay, then that's all. We're a little bit early today. I wish you good luck for the exam. So if you have any more questions, just write me an email. Then maybe we can, if it's too complex to be answered in just one email, might be possible to do a Zoom meeting or something like that. So just let me know. Good luck for the exam and thank you very much for your attention.
No, I'll see you then.
Okay, yeah, ask me again.
Okay.
Quickly. It's fucking up.